we're going to talk about Blue Gene. So what Blue Gene, as I was just joking about, is a whole family of machines. And where did it come from? Well, IBM originally was looking into special architectures targeted at protein folding. So that's where the gene part comes from. And I think we know that IBM's favorite color is blue. So that is where Blue Gene came from. And the first Blue Gene in 2004 was Blue Gene L, and I believe L was for light. Livermore eventually had a very, very large BGL system. Argonne was only at that time dipping its toes in the water in 2005 with a one-rack system. And this came from the start of the process where there would be not one leadership computing facility at Oak Ridge, but two. Another one at Argonne, where the Oak Ridge site would, at least initially, have Cray-based platforms, and Argonne would have an IBM-based platform. So with at that time, even though we only had a one-rack BGL, it was a fairly uncommon machine, and we had a lot of community training meetings where people were somewhat like yourself were invited to come and explore the new architecture. So of course things don't stand still, and while Blue Gene L was in the field, we were working in a three-way collaboration with IBM and Livermore on the next generation, which became Blue Gene P. And I'll talk about that about 2 slides down. And that culminated in Argonne getting its first massive system, Intrepid, the Blue Gene P, in 2008. That was 557 teraflops. And of course, as soon as we plug that in, we started working on the successor, because these cycles take about 5 years to turn the crank on. And that became what is the current system, Mira, which is 10 petaflops. We had actually hoped for enough funding for a 20 petaflop system, but we had to settle for 10. So, despite the fact that Blue Gene Q, Mira, is 3 years old, in the last 11 years, Blue Gene architectures, whether LP or Q, they've been in the top 500 number one about half the times in the last 11 years, and that's quite phenomenal for an architecture. It's really 3 architectures, but in that family. And I think that's an example of how successful the scalability of it is. Even now, being 3 years old, as I said, Blue Gene Q has 4 entries in the top 10. So it has not been displaced by newer machines all that rapidly. And Scott noted here that Blue Gene has been number 5 on the Green 500. I seem to recall that we may have hit the top at some point, but I'd have to look that up to be sure. So, what makes a blue gene a blue gene? So this is the DNA, so to speak. I think there may have been a little joke in there about this, but besides being incredibly powerful, but what design philosophies get us to that goal? So the core essence of it is that you should have high efficiency, trading off low clock speed or lower clock speed for more efficient flops per watt, and smaller computing elements distributed throughout the machine, as opposed with the ratio of compute to memory should be more in the direction of a processor and memory type of system than it is to have huge fat nodes. And because when you clock things much faster, you start losing heat. There's a lot of power inefficiencies when you clock things up. That's why processors in general have hit a wall, and why multi-core and multi-threading have been, the approach that industry has taken. So Blue Gene embraced that idea very early, and that's the philosophy in a single core or node. But the other half of the equation is connecting them together with a very fast communication network. And in the Blue Gene case, it's been a torus, whether it was three-dimensional torus in the BGL and BGP or five-dimensional torus in the BGQ. And from a system design standpoint, the compute power, the communication bandwidth, and so forth, they need to be balanced, because there's no point in making processors so powerful but you can't get the data communicated between them. Right? So system balance in a large, massively parallel system like this is important, because these things cost a lot of money, right? So you don't want to put resources where you don't want to put money to get resources that you can't take advantage of. Right? If you double the speed of the network, then the CPUs may not be able to pump enough data into it. So the network's idle. So what's the point? Right. So other things that are important in a massively parallel system are being able to code it easily, of course, and high reliability, right? Because when you have a system composed of literally millions of pieces, even a small failure rate can keep the system down. And Blue Gene has had a lot of engineering effort into reducing the component counts, putting the entire system on a single chip. There are no, by and large, there are no sockets, right? Within a node, no chips are socketed. Sockets actually create a failure point that at this scale is not good, and things like that. So as I mentioned, there was a collaborative effort between IBM and Argonne and Livermore to create the BGQ, and many aspects of its design were decided upon during this collaborative phase. Certainly, the basic chip capabilities, which came from a PowerPC, were not really on the table to change, but especially within the realm of system software, we were able to provide a lot of input, and that includes user APIs to access certain hardware functionality. One place that we did have some considerable input was on the hardware performance counters, which on Blue Gene P were somewhat lacking, and with our input and Livermore's input, IBM came up with quite a good performance data collection hardware support, and I think it will be something that we'll miss when we move on to the next architecture. So speaking about comparisons of Blue Gene P to Q, this table summarizes the factors, but the short version is, of course, you will have these slides online. I can't possibly cover all the details in them, but I'll just say that the number of cores per node increased significantly. The more importantly, within a node, the ability to have different cores access the same memory coherently was added that allows BGQ to do threading in a real and proper way, and not just as a mechanism for parallelism instead of MPI ranks. And the clock speed also increased quite a bit. So what did that overall system design going from BGP to BGQ get us? Well, on a set of applications that are from real applications, some of them may be kernels, as you can see from this example list, the ratio of performance on BGP to BGQ goes from something like 5 to a factor of 5 to a factor of 11. The system that you're using for your most of your experiments or coursework here is Vesta, and Vesta is kind of off on its own as a system. And the other systems, Mira, Cetus, and Cooley, are grouped together on a different file system, right? So the large Blue Gene and Cetus, the development rack, in a way that's the debug queue for Mira, and Cooley, these all share one file system, and in some ways are a unified system, and whereas Vesta is off here on the side. So now we'll take a dive into what are the components in the Blue Gene, and kind of work our way up from the bottom up. This compute node, this is actually much larger than life size. It's only about that big. It's kind of like an accessory card for your PC. And as you can see, the entire system is on this chip. It's soldered in, and pretty much the only other chips on the board are RAM. That goes into this larger board. It's about the size of a pizza box. And then 32 of those go into this rack, and that gives you 1024 nodes. So this is the same information, except that what we saw on the previous slide was this is the rack full of nodes, but there are other nodes for I/O, and they're functionally equivalent, but they're not water-cooled like the compute nodes. These compute nodes are actually water-cooled. And these I/O nodes, which live in a different type of drawer because they're a little bigger, they're the same processor, the same memory, the same everything, except they're just not water-cooled, and that they're in a different cabinet because it gives them room for the PCIe cards to talk to the file system. So from an organizational standpoint, the compute nodes only talk to the outside world through those I/O nodes. Okay, and that's how they get to the file server. The way that the programs are actually started up is through system software that in the service node, it's just a Linux machine. The service node tells the I/O nodes, hey, we're going to load this program. They get it from the file system, and then they dump it onto the compute nodes and tell them, okay, guys, time to go. So looking closer, it's all packed onto that chip. Each one of these is a core. Laid out here, there's the connections to the RAM on the outside. The Taurus network routing is here, and there's a crossbar switch that connects the cores, right, the PUs, to the sections of the L2 cache, and we'll see that in this slide, right? The cores are all laid out here. Each core has an L1 and a prefetcher, and this crossbar connects them to these slices of the L2, and then those chunks of L2 go to two different banks of DDR. Within the core, you've got this whole thing is one core, and you've got the instruction fetch and decode going on here. And I'll just say that this is the part that handles the integer instructions, and this is the part that handles the floating point, including the quad floating point vector units here. Now, when this core, it's an in-order core. There's no rearrangement on the fly. And you can have 4 threads running, 4 real threads running, hardware threads. But in a given cycle, you can only tell the integer unit to do something as well as the floating point unit to do something. And there is a limit in this core because it's a simple core. Remember, it's a low power, simple core, that in a cycle, one thread can only try to do one thing. So the take home on this is that in order to keep both the integer part and the floating point part busy, you need one thread to issue an integer instruction, or I should just say a non-vector instruction. There are other, you can see exactly what's in there. And another thread, a different one, to execute a floating point instruction. And so without 2 threads doing this in every cycle, you're not maximizing the single core performance of this particular core. Okay. So if you're running one, let's say just one non-threaded MPI rank per core, you are guaranteed to have no more than 50% of peak on that core. Even if you put 2 MPI ranks on it, the 2 MPI ranks will be implemented as 2 threads. Now you have some hope of getting above 50%. And the raw computing power in this system does, in fact, come from being able to execute that floating point for 4 wide floating point operations. And if you're doing something like fuse, multiply, add, you can actually get 8 flops in a single instruction. I mentioned the L1 cache attached to each core. It's not very big. Because remember, one of the goals here was to be able to do threading and have cache coherency and so forth, and that's implemented in the L2. Right, so the L1 is small. It does have a prefetcher, and the prefetcher is somewhat interesting in that you can program it. So normally, as any prefetcher, it will try to anticipate what is next, the next memory references you're going to make. But this one actually has another mode that you can control under program control. Where you can train it to, let's say you have a loop, and the first time you go through a loop, you can say, hey, pay attention to the memory references that I'm making as I go through this loop. Okay, here's the beginning, here's the end. And then tell it, I'm going to repeat the loop. You prefetch, because I'm going to access the same patterns, it will try to prefetch the same pattern as on the previous loop. So depending on your code, that kind of thing can be quite effective. So moving up the next step in the architecture, the crossbar gets you from the L1 to the slices of L2 with various bandwidth. And you're sharing things, right? So if multiple cores are hitting the same part of L2, or multiple L2s are hitting the same bank of RAM, right? Then those will be your bottlenecks to ultimate memory performance. This is another diagram of the L2 with various properties of it. I'm going to have to skip the details. So we've pretty much covered what goes on inside a single node. So now the question is, how do the nodes talk to each other? Well, BGP had a 3D torus network, and BGQ has a 5D torus network. Now, to be fair, the 5th dimension is only among pairs of nodes. Right? The 5th dimension's extent is only 2. And so you could think of it as a tightly wound part in the string theory. It's very easy in terms of hardware and wiring to scale this to a very large machine. However, you'll have to note that you can't just take any old rectangular chunk of the nodes and expect to be able to have torus wraparounds in that, right? Any rectangular chunk of the machine will have a mesh network in 5 dimensions, but it needs that wraparound to get to the end. So the units that the Blue Gene Q uses are half a rack, 512 nodes, which is shown as one of these chunks. They have the wiring to wrap them around. And then between cabinets, there are external cables that connect these so the half rack is called a midplane in BGQ lingo. The midplanes are connected with these external torus wires. So BGP actually had 3 distinctly separate networks. BGQ actually only has this one network. The reason why BGP had it was it had dedicated networks for collectives and barriers to speed them up. In BGQ, there's only not one network, but it has virtual channels in it to accomplish those functions. So from each node, which I guess you can't really see them, they have the links in 5 directions for the 5D torus, plus and minus in each direction. So that's 10 links total. But there's an 11th link available, and it's not used on most nodes, but in this, in any partition, okay, it's not, this midplane is actually composed of smaller units. They're not, they're non-torus connectable units, but in each hardware partition, let's call it, 2 of the nodes are nominated to be called bridge nodes to talk to the I/O nodes, and they use that 11th link. Let's see. This gives some stats about the torus network. You can and going back to the balanced issue, you can actually achieve a very high portion of the peak of the network performance with this system. And we'll look at the network interface and the router are 2 parts within the system chip, right? Sitting there along with the cores. Remember, it was in the bottom middle of the photo of the die. And this is the part that's sort of closer. Remember the crossbar switch that connected the cores with the L2s? Well, this messaging unit is also hanging off of that, and this is the router unit. And these are the links coming in off of the torus, and these are the links going out. So when something comes in, if it's headed for this node, it will come in and get routed into a receive queue. If it's coming in and it's headed for another node, it's just an intermediate hop on the network, it won't go in anywhere. It will go from the receiver and then go right back out again. So it passes through with very minimal, it has no interaction from the cores on the node. It's a true router functionality. And things that come out of the cores on the node through the messaging unit here will then get injected into the torus and come out. They'll come through these FIFOs and then go out right onto the torus. Let's see. So besides talking to each other, the nodes will need to talk to the outside world at some point. And this is actually the first place where there's any possibility for external interference, because until now, the job has been using the nodes specifically set for them, and that there is actually no contention on that subset of the torus from any other jobs, right? So now when you go out from the compute nodes to talk to the, they have dedicated I/O nodes, but the I/O nodes going to the file system will now be using shared resources. And I was mentioning before the bridge nodes. So let's say the hardware partitions in Mirror are actually 128 nodes. That means that for every 128 compute nodes, there is one I/O node. But it's not quite as, the mapping is not quite as straightforward as that. 64 of them are connected to one I/O node, and 64 of them are connected to another one. So by these, so now there's 2 compute nodes are nominated as bridge nodes, and half of the compute nodes go through that bridge node to talk to the first I/O node, and the other half of them go through the other bridge node to talk to a different I/O node. However, this 128 node partition has a partner who has the opposite assignments, so that the partner partition is connected to the same 2 I/O nodes, but sort of vice versa as far as which one's the primary and which one's the secondary. So, but the point though is that the set of 256 nodes will use 2 I/O nodes, and there won't be any contention, there won't be any sharing of the I/O nodes with any other sets, right? You just have this pair that share a pair, and so on. And when you get, when you think about it from the size that you can queue a job, right? In terms of the hardware, this 128 node is the smallest partition on Mira, but because the system is so large, you're not actually able to run, because of administrative reasons, we've set up the machine to not run anything smaller than 512 nodes. So that's why you've seen it said that the smallest job you can run is 512 nodes on Mira, but in fact, if things were defined in system definitions slightly differently, it would be possible, given the hardware, to run down to 128. But there are so many 128 node partitions in the machine, it would become a very unwieldy situation, and that's why they're not set up. The BlueGene software, right, we've talked all about hardware, and I'll just say a few words about software. Scalability was a goal, and open source wherever possible was a goal, and being able to leverage the hardware features that are particular to the machine was, of course, very important. So we ended up with a system that everywhere except the compute nodes use Red Hat Linux. That includes the I/O nodes and the service nodes and so forth. The compute nodes themselves use a stripped down kernel called CNK. It's Linux-like, but it's only runs, it's not multiprocessing, it only runs your program. There are literally no other processes running on the compute node, and that's why it does not support things like fork, because it only runs one process. And the reason for that is to reduce jitter and prevent skew when you do barriers and things like that. Let's see. These are some of the special features in the BlueGene architecture. We've mentioned most of them, and they're mentioned here because they are, in the end, accessed by some software constructs. So there are support in the L2 hardware. I didn't mention earlier that yet another thing that the L2 can do is to support fast atomic operations. And there's some API mentioned here. There's a some hardware in the node called a Wakeup unit that reduces the time that you would spend looping, busy waiting for conditions to happen, right? So you could take advantage of this, or very often, the compiler will generate code that can take advantage of this. And I already mentioned the hardware performance counters, and they there's a diagram of how the data flows around in a loop to get to the collection place. And there's a whole API to do that, and we have documentation for that. And the last feature I'll just mention is something else that's implemented through a special hardware in the L2, is that the L2 supports versioning, so that you can actually have more than one version of memory contents for particular pages. And what that lets you do is support in hardware transactional memory. So where, let's say you are making a decision and you don't know, you're in a loop and you're not sure because of the analysis of the code whether there's a cross-loop dependency or not. So you would be able to run it if there's no dependency, and you would not be able to run it if there was. So what you could do is to just say, well, I hope that there's no dependency, and execute the code. But at some point later, you may have a conflict and say, oh, there was a dependency after all. So because the L2 had two versions of what was going on, you can roll it back as if you hadn't done the operation. And then if you only roll back 1 in 100 times, then you've probably accomplished something good, right? So that's the speculative, and when you have to implement something like that in software, it's much too expensive to even think about doing. So that is the last slide that I've managed to squeeze into this whirlwind tour of BGQ.
Okay, so when you get new BGQ machines, what do you do with old machines? Do you give some universities? Or?
So the last one, a few racks of it were donated to a school. Most of it was actually sold for scrap. Now, it's an interesting thing you should say it that way, because there will be no more blue jeans. The blue jean queue is the end of the line of the architecture, which I think is unfortunate, but on the other hand, the architects of the blue gene are now at Intel and pursuing parallelism in slightly different but also interesting ways.